Thank you very much for joining us for this BCO webinar on making the future workplace, materials and methods towards a circular economy. This is an overview of the research paper that was published by the BCO towards the end of last year. I believe the original plan was to deliver a series of these across the country, but we're obviously having to adapt, as you all are, to the current situation, and hopefully it's no less effective. I'm going to start off with a quick introduction to the team. I'm Ed Harris. I'm a senior architect at Alford Hall Monaghan Morris. You'll hear shortly from Rob Partridge and Christopher Blust, who are Director and Associate Director at AKT II, followed by Professor Derek Clements Kroom of the University of Reading, whose birthday it is today as well. So happy birthday to Derek. Now, along with my colleague Stephen Taylor, who isn't able to join us, we collaborated on this research paper over the latter half of 2019. Rob will give you a bit more of an introduction to the research, but first I thought it might be useful to give a bit of context, particularly as a lot has happened over the last few months in this field, and that's even before coronavirus has hit. It's also worth noting that you can offer up some questions via, I think there's a Q&A button at the bottom of your screens, and we'll try to answer those at the end. I think we're going to try and spend about 45 minutes presenting, and then hopefully we'll have about 15 minutes for Q&A. So feel free to fire in your questions. Okay, I'm going to make a start then. Hopefully this will work. So yeah, just a quick preamble. I'm going to start with just the UN Sustainable Development Goals, which were set out 5 years ago to be achieved by 2030. So we're a third of the way into that process. And many of you will be familiar with these. Many of them have construction-specific properties, and particularly also because they are now beginning to spawn a whole series of knock-on documents, such as these from the RIBA, issued over the last 12 months, and including most recently on the right there, the new plan of work that directly reflects the UN Sustainable Development Goals. We've also had various campaigns in the recent months, such as the AJ's Retro First campaign, which advocates the reuse of existing buildings rather than new build. And we're being bombarded by carbon calculators, such as this one, which was developed by Autodesk, Arup, Skanska, Katera, and Microsoft. The week before we published, we discovered that the City of London were going to require a new circular economy statement for all major developments, illustrated rather nicely by the doodle on the right there as a concept. And then we've also had the London Energy Transformation Initiative, who, since our research was published, they've put forward this operational energy summary, how we can reduce operational carbon, but also a whole design guide for carbon reduction. I'm going to hand over to Rob now.
Thank you, Ed. Good morning, everybody. So as Ed said, the thinking around this actually started quite a while ago. Myself and Derek sit on the BCO research committee, and we realised that perhaps there was a little bit of a gap in terms of the research papers with respect to kind of the technical design aspects of sort of thinking about what the office of the future would look like, and with particular emphasis on materials, how we should choose materials, how we use materials, and obviously how we build with materials. We roped in AHMM because, as many of you know, we collaborated with those guys on the design of our office, the White Collar Factory, and we'll talk a little bit about that later in this presentation. And as we started to think about the kind of the contents of the paper, this diagram that you see on the screen started to come together. And I think it's worth mentioning that we didn't set out to write a sustainability paper. We set out to talk about design. And I think it was interesting that this kind of circularity diagram almost seemed to come out of the sort of the subconsciousness, if you like, of all the design agendas that we were all discussing. And it really did kind of envelop everything that we thought was important to discuss. And also, as I say, it defined the contents of the paper. And for those of you that have seen the paper, there isn't a linear contents page. This is the contents page. So the whole research was very much driven by graphics and infographics, which I think is a first for the BCO. So we were quite proud that we were changing a little bit of that presentation style. And as you can see in that diagram, we sort of start with number 1, which is all about future proofing. We think that whenever you work on a project, you should think about flexibility first, before you even think about maybe what materials it's made of, which is number 2. And then we should think about how we can use those materials more efficiently. Then number 3 is, of course, how you build the building, how you make it. Number 4, loose fits. That's all about kind of how we respond to the churn of tenancies. Then number 5 is all about kind of data and how we embed data and how we can use that data appropriately. I still think we're not doing that anywhere near enough in the buildings and the projects going forward. And finally, number 6 is reuse. And that's obviously looking at kind of existing stock, but also obviously drives back into number 1 there with respect to designing for flexibility and adaptability in the first place. The other concept that I just wanted to touch on, Ed, if you move to the next slide, was about, again, just talking about the circularity argument. I think traditionally, in terms of environmental issues, the industry has looked at that subject in a very linear and traditional way, with production, construction, and usage. And certainly as structural engineers, we've been sort of sat around the table for the last decade, really listening to conversations about energy in use, which is obviously very, very important. But the whole circularity concept, Ed, if you switch to the next one, is far more complicated than that, because it is all about the fact that we need to look at, how we dismantle, how we reuse, and how we recycle materials. And of course, if we can extend the life of a building by designing it adaptably and flexibly, then you're obviously off to a better start in the first place. So again, this diagram and this kind of thinking, again, started to kind of really sort of drive all of the agendas that we're now going to discuss. So I'm going to hand over to Chris, who's going to start with section number 1, which is all about future proofing.
Thanks, Rob. So as Rob said, future proofing is really the enabler to reuse, which is step 6, which we'll get to. But before I start talking about specifics about future proofing, Ed, if you go to the next slide, I just kind of wanted to touch on a small case study that we do talk about in the paper. And this is a building that was built 222 years ago, Shrewsbury Flax Mill Maltings, which sits on the edge of Wales. And it really is, the testament to the focus of this report. So this building was actually very experimental. It was built by Thomas Barge back in 1797. And Mr. Barge was, an architect engineer, as you were back in the day. And he experimented with cast iron. And he was actually also involved in Iron Bridge just down the road. And his whole idea was to build a building that was effectively fireproof. So obviously in 1700s, a lot of these mills were burning down. Timber was obviously used widespread. And so he was looking for a solution with a cast iron frame, which was effectively fireproof. And so it was this technology actually that was then used further on in the construction of the first skyscrapers. And so Shrewsbury Flax Mill Maltings is actually known as being the grandfather to skyscrapers, which is quite interesting. So in this building's 222-year life, it's actually had three lives that can be broken down into kind of 100-year periods. The first period, it was used as a flax mill, so heavy machinery. 100 years later, it was changed to a maltings, and now it's actually being rescued by Historic England, who are refurbishing it and actually turning it into office space, which is quite amazing. And this building is a testament really to this paper, because it's been built and constructed in a way that you've been able to kind of adapt it and remold it into something new. So just go on to the next slide, Ed. So if we want to talk about this concept of flexible space and adaptable buildings, I think everyone can kind of start to understand that a flexible space is something that's becoming quite standard in a client's brief. We're seeing that every day. Something that we really should be aiming towards is creating this concept of what is an adaptable building. And when we say adaptable, it means small incorporations to make it adaptable. So for example, that might mean pre-drilled bolt holes in beams and columns to enable it to be strengthened at a later time. Building things to measured modules so that you can reduce waste. And then also potentially incorporating soft joints so that when you do need to replace something, you're only replacing a small component or a small piece of it. So essentially designing for disassembly. Next slide, Ed. And if we just kind of think about the standard base build specifications, what we're seeing in the industry at the moment is that these base build specifications are actually kind of being siloed together. So if you think about Google or Facebook, for example, we're seeing that their offices are actually a combination of traditional, collaborative, and academic spaces. And so again, these things are all basically becoming one. And if we actually just think about life sciences, actually life sciences is a perfect example now, kind of living in the COVID-19 era. What we've been seeing even before life sciences was that, before COVID-19, we're seeing life sciences actually moving into urban centers, kind of away from their traditional approach of being kind of outside of the city in these academic campuses. So what can we do basically to enable the life sciences to move back into the city? Obviously, they have a lot more stringent requirements in terms of loading and vibration to be able to take a traditional office, for example, and be able to adapt it very easily, very quickly to make it a life sciences center. So Ed, next slide. So what we've done in the report, we've kind of highlighted kind of 4 items to contemplate. The first of those is to understand the design life and the permanency of each component in the building. So for example, if we look here, each component of the building, obviously structure being the largest component of that, is actually thinking about the scale of the structure. It's actually quite cost effective to build. It's not very expensive, but it's the biggest component. But it's hard to modify later on if you don't build in these adaptable items. And you compare that to services. Services you're going to be replacing probably 4 times or 5 times in the life of the building. And the services are a big component of the cost, obviously. So next slide, Ed.
Yep. So many of you will be aware of this, so I'm not going to dwell on it, but critical to this design for future proofing, and particularly with these sort of goals that I outlined at the beginning, is a passive approach to operational energy, and ensuring that is sort of ingrained in the sort of core of the building fabric from the outset. And the document that we published sets out three sort of phases to that. First being really understanding the sort of local environment, understanding what you need to sort of harness and what you need to reject. The second aspect then being getting a better understanding for what you think are acceptable internal conditions and internal criteria. It's not necessarily sticking to a single figure. It's just being a bit smarter about the way we think about how people use the space and how people can be comfortable in that space. And then the third aspect, as I said, is really a sort of holistic approach to the design of the building to ensure that it's working at, as hard as possible, and every part of the building is working sort of together. And by sort of embedding a lot of that sort of passive design in the fabric, I'm just going to go forward, such as external shading, having a structure providing that, or having thermal mass provided by concrete slabs. Having that ingrained in the building gives it a better chance of that passive strategy lasting the test of time. Just going back a slide, I'm driving, so I've got the benefit of being able to chop around. But this is just useful. It's come out of the RIBA 2030 climate challenge, just looking at how we are actually going to try and achieve some of these targets. And we talk about, shortly I'm going to talk about white collar factory, but it's worth understanding that which is fundamentally being designed around kind of passive design, is only sort of really operationally is only really sort of hitting around the 2020 sort of targets for operational energy. In terms of 10 years from now, we're really going to have to be really ramping up the way we design these buildings to act as passively as possible. And then the fourth aspect that we talk about in this section is enduring character, and we set out four kind of aspects which we've often found when working with developers can be kind of make or break between a building being retained or or being rebuilt. The first bit being volume and flexibility, not necessarily inherent, but with the potential to at least add or create some volume and flexibility with the sort of shell that you have. The second being daylight, and being able to maximize daylight penetration into the floor plate. Third being opportunities for external amenity, whether that's roof terraces or additional terraces. And the fourth being a sense of place, and that's where we're really talking about the ground floor experience and being able to have a gone are the days of the sort of defensive office building. Now the focus is very much on a welcoming ground floor experience, a dynamic variety of uses, and keeping staff happy as much as anything. These are sort of two examples which we've used to highlight the volume and flexibility part of that. The building on the left, this is actually sort of a concept image that we used for the post building, which we've just completed in central London. It was a sorting office with some incredibly generous floor-to-floor heights, and rather than ditching that, reducing the floor-to-floors to more standard heights, we actually encouraged the developer to actually maintain them and actually have the potential to input mezzanine levels sort of around the cores, and then the new builds, which happens sort of on top of this part of the building, also retain some of that character. The right-hand image is actually the Bower building, again, just off Old Street roundabout in London. the sort of grey fabric, the grey structure in the centre of the building is the existing. And there we've actually got the opposite problem. The floor-to-floor heights are very limited, and the initial concepts, which has now been followed through, is that additional double height spaces would then be almost sort of bolted on to the outside of the building to give some kind of relief and some sense of sort of joy and flexibility and openness to those spaces. And then throughout the document, we've got a series of case studies, and this one is particularly useful, being as it is the original broadcast building for the 2012 Olympics, which has since been adapted by Hawkins Brown to a huge variety of different workplaces. And it's really the sort of incredibly flexible long span structure which has enabled this, alongside you know, an intelligently sort of designed facade which incorporates sort of frits to the glazing, and you know, the ability to bolt on external amenity space. This is sort of really all epitomizes everything that we just talked about. And then section 2, we're talking about you know, if you're faced with a new build project, you really want to make as much happen with as little resources as possible. So doing more with less, you know, as much as possible with as little as possible. And we start this off. Oops, excuse me. With this diagram, which again is an RIBA diagram from about 5 years ago, but it really epitomizes the sort of principle of investing as much design effort as possible in the sort of core fabric of the building, to then enable it to go through the sort of the cycle as illustrated there. And that is kind of what happens at the White Collar Factory. So it was sort of born out of hard times in 2008, and was originally a sort of research project into what, you know, could be a sort of optimum office. And out of a you know, a process of design, working with AKT and ARUP, it came up with this concept for the White Collar Factory with a sort of standard floor size, and then facade modules that adapt to different orientations. And born out of that were these 5 principles. First being tall ceilings to sort of maximize daylight penetration, you know, get an even distribution of light as well, of artificial light. Smart servicing, so services which are actually embedded in the concrete slabs. So you know, we've got natural cooling occurring, as well as the potential to sort of upgrade that where needed for more intensive cooling. A simple passive design, passive facade rather, as outlined in the previous slide. So different facade types responding to different facade orientations. And critically there, and particularly something that we'll probably come on to later, the ability to open windows. And some of you may have seen some of the work that's been done by the BCO recently in terms of responses to coronavirus, where, you know, the ability to open windows is seen as a really important factor, and I think it is something which is going to be here to stay. Then we've got deep plan floor plates, which, you know, enable multiple tenancies and you know, maximum flexibility. And then in this building we had a concrete structure to really maximize that thermal mass. And then over to Rob.
This is a graph which has been driven by many assumptions. And on the left-hand side, you can see kind of the traditional structural materials, concrete, steel, and then concrete where you have a larger degree of cement replacement. And then on the right-hand side, you can see the impact of using timber. And that's timber, not just on its own, but timber combined with other materials such as concrete and steel. And you can obviously see the trend line. Now, what I wanted to say here, which is really interesting and which we find a very dynamic debate, is that of kind of the circularity aspect again. So it's not just about the embodied carbon that you use to construct a building, it's more about the embodied carbon that you're going to use or not when the building gets to the end of its life. So at the moment, we all know, I'm just going to ask my other colleagues, can you hear me okay? Because my computer is telling me that my internet's dying. Yep, good. Yes, so the interesting thing here is about reuse and the assumptions behind reuse. And, you know, we know how much concrete is recycled these days. We know how much steel is recycled, though that actually a lot of the recycled steel does not end up in structural steel work, which is being reused. It's downcycled. But we don't actually know what happens to CLT or other timber engineering timber products, because we haven't really demolished that many new timber buildings at the moment. And actually, as these assumptions change in terms of reuse and recycling, you get huge swings in this diagram. Other aspects that are very important is what Chris and Ed have already talked about in terms of adaptability. Because if one building lasts for 50 years compared to another building that lasts for 100 years, again, that again will massively swing this kind of trend. The other graph, which Ed will go on to now, just looks at kind of how this trend line changes when you start to change grids. And of course, there are many variables that you can start to play with. And I think that, you know, again, we could talk for hours and hours about this, but we thought that in light of what's happened in the last year, that this was a really important aspect to kind of weave into our presentation today, to kind of open up the debate a little bit more about the choice of materials. Back to Chris, I believe, guys. Oh no, still on me. We threw this slide in because we didn't want to give the impression that timber was the answer. We wanted to be very honest that timber is part of the answer. There's our esteemed leader, Hanif Kara, there on the right, leaning against a timber column. And you can see there that, you know, sometimes timber is not appropriate to be used as a compression element, for example, because it does get rather big when compared to concrete or steel. And so a lot of our structures where we use timber do tend to be combinations. So you'll hear engineers talk about hybrid structures more and more lately, where we try and kind of use the best properties of steel, brick, concrete, timber, and effectively combine them to create a sort of an optimum holistic design. We talked to various timber architects during the course of our research. Shigeru Ban on the left, who tends to be very traditional with his jointing and tries to reduce the amount of steel and uses hardwood connections with softwood elements. And then the next slide, we've got some examples of Andrew Warr's work with Wall Thistleton. The one on the left there is a hybrid solution of CLT and steel, which is down in Shoreditch. So, you know, that example is very pragmatic. It's a very slender structure, and it's using the best properties of steel and the best properties of CLT to actually produce a really rather efficient office floor plate.
And we thought we'd actually throw this one in. This is a few photographs out of a fabrication shop where we were actually putting together two different types of timber. So again, you know, this is really along the lines of more with less. also using a hybrid structure, because these fins you can see on the right-hand side are actually using a combination of softwood with a hardwood core. And so we put these hardwood cores in to be able to take kind of the peak stresses and shear that needed to be transferred. So we thought it was an interesting example of how you can still use timber with timber, but make it work the way you need it to. And if you go on to the next slide, Ed. Again, Ed mentioned that we do highlight case studies throughout the report, and we thought Sky Central was an excellent example actually of a hybrid structure, doing more with less. And so in the image here, you can kind of see this really long spanning timber roof structure, but below that, all the intermediate structure is timber with steel, which is an excellent example. This building actually won the BCO 2017 award for Best of the Best and Best Corporate Workplace. So that brings us to kind of the third chapter, which we call Make Modern Methods of Construction, or MMC, as you might know, or DFMA. And I'm sure many of you are actually familiar with the advantages of using this style of construction. Effectively, how we see it is there's three ranges across MMC construction. On the left-hand side, we have kind of elemental construction. And it obviously has more kind of intrinsic pieces. It's more expressive. And we're kind of calling that, it's more micro scale MMC. Whereas on the right-hand side, this is fully volumetric construction. These big components come to site and they effectively just got stacked on top of each other. Some of you might be familiar with 101 George Street in Croydon. I think it's 45 stories of volumetric construction, and I think it's actually the world's tallest volumetric tower. So there's actually amazing things that you can do with it. This slide really just highlights the benefits, especially in terms of traffic and lorry movements that you can have on your site. It's obviously more along the lines of resi construction, as you can see here, CLT frame, precast walls and slabs, but there is actually hybrids of these systems being developed, which I'm going to talk about in a minute. Before that, actually, the paper explores this concept of micro and macro construction, MMC construction. Sorry, next slide, Ed. So if we think about it, little pieces of plant are actually pre-assembled components in a factory which come to site. We call that micro, but then on the macro scale, you can think about completely pre-assembled plant rooms. And you might think, macro MMC is obviously better, but I think that's actually very subjective. We need to think about disassembly and again, reuse kind of going ahead. So if something comes in a very large component and a small element of that breaks, you need to replace it. You don't want to have to be taking out that entire macro element. So we need to just be thinking about disassembly as we kind of go ahead. This is obviously fairly relevant also at the moment, kind of in the COVID-19 era. So some of you will probably have noticed how China actually built quite a large hospital. I think it was in 2 to 3 weeks. So amazing kind of potential, which kind of shows how this kind of construction is kind of needed in kind of these emergency situations. So in this chapter, we don't actually do a project case study. We actually did a company case study, and we did that on Mace. And a lot of you will probably be familiar with their factory MMC kind of technologies they kind of pushed a few years ago, which was quite interesting, and moved away from that now. But they do call the Mace factory basically a genesis to what their new method is. So recently launched just in December is actually the Mace high-rise solution. So if you just flip to the next slide, Ed. The HRS system is actually quite simple, but quite ingenious, to be honest. It's a series of precast planks with pre-bolted facade panels it still kind of offers the same benefits as the previous mace factory kind of setting, because as soon as that panel is installed with the one above, you have an entirely enclosed space, so your dry trades can come along. They are building a residential building at the moment, kind of in Stratford at the moment, but there is long span steel beam options available for offices, which is quite interesting. And then on the right hand side here, you can see a bit of a small BIM model. But what Mace is also doing along with this is actually creating a digital twin. And so every single component is actually tagged, and that tag can be scanned from stage to stage, from being delivered to being picked up with the crane to being dropped with the crane. And so that actually really allows them to collect all of this kind of big data and analyze it to, you know, from everything to see how productivity is going, and to also kind of speed up the construction process. And that's it for MMC. I'm going to hand it back over to Ed to talk a little bit about loose fit.
Okay, so yeah, loose fit is about fit out. So this is particularly important in the context of that. I think Rick's have stated that a commercial building will typically have 30 to 40 fit outs over its life. So this chapter really focuses on sort of maximizing fit out, flexibility of fit out, and trying to minimize waste as much as anything. So just starting off with these three images. These are some images that we would typically create for a commercial, speculative office. And they're important just because we're moving away from a typical Cat A fit out, which is probably more like the image on the right, where effectively, ceilings go in from day one, and then day two they'll often end up in a skip outside, which it still does happen, but it's becoming increasingly sort of difficult to justify. So we produce these sorts of images to try and set out that actually, if you get the building to look and work well, just as it is on the slide on the left, it can then be augmented in different ways according to different tenants' requirements, whether it's with rafts or full ceilings, or ceilings within meeting rooms, or however. But it's making sure that the starting point gives the best basis for that to happen. And we came across some research that UCL have done about waste in fit out, and these graphs really sort of outline some of the key things. So the pie chart on the left showing that gypsum was plasterboard was the sort of key waste material, the majority, 30%. Metals at around 15%, which I think we thought was likely to be ceiling panels. And then the graph on the right is showing how the kind of various waste streams work out. So it does show that the majority of waste collected from fit outs does end up being recycled, which is obviously great. But obviously each of those phases, whether it's through transport or through processes, does require energy and resources, and significant amounts in some cases. So wouldn't it be better to try to eliminate as much of those as possible in the first place, in the sort of base design? And here we're just jumping into two case studies, which we've done. One for this one for Google, which you can just sort of make out in at the top, effectively is a sort of stripped out ceiling and services strategy, which is then supplemented by these sort of pods, for want of a better word. And each of these pods is effectively demountable by 1 to 2 people. So it's been made with plywood modules, which are all easy to assemble and disassemble and relocate. So they can be used for meeting rooms, or for VC rooms, or for breakout spaces, or concentration rooms, or for whatever other weird and wonderful things Google can come up with. And then this other example is actually back to white collar factory. So again, similar principles, but rather than a sort of modular cassette system, this is then actually, again, plywood based, but for a very different type of operator. So this is for the office group, where rather than sort of pods, these are more used in sort of traditional partition way. So you can actually just about make out a partition, a metal partition frame at the base of those timber partitions, with then standard studs. And again, this is all based around a standard size of plywood, so minimizes cutting. None of the plywood is cut unnecessarily, and also enables them to be taken out and relocated, which works particularly well for the office group's model of enabling occupiers to expand or contract, or chop and change on a quite regular basis. And then we move on to section 5, which is just about how we occupy buildings, and particularly sort of important in the current situation, and in the context of how we get back to work. These are 3 pie charts which you may well have seen before, but they really outline how in an office the majority of carbon emissions are in its operation, rather than up to practical completion. So it really highlights that the operational emissions of the building are paramount. And then we go through picking up on some earlier research that BCO have done on smart strategies, and how some are, by enabling the shell and core of a building and putting a bit of effort into that, it can then enable AKT sort of bolt-on technologies to be maximized. A really good example that we refer to again from the white collar factory is how the concrete frame is providing this fantastic thermal mass store for the building, and then this sort of short and sort of fast response is that there's a traffic light system which then tells you when it's suitable to open or close windows. And AKT, who are in that building, will hopefully have some positive stories about how it's used. Chris is smiling. And then next, we also touch on well-being, and this is taken from some previous BCO research called Wellness Matters, which Derek authored. And again, just the way it's broken down, and also it relates to the WELL standard into kind of shell and core, and those sort of embedded strategies then can help to allow for additional sort of top-ups and bolt-on strategies to be really maximized. And what's interesting, I think, at the moment is there's going to be a sort of real sort of tension between, as we go back to offices, between, for example, having windows being openable, and I think we're going to be encouraged to have windows open as much as possible, which was obviously going to put extra strain on mechanical systems and possibly operational expenditure, carbon expenditure during that time. So it'll be interesting to see whether that is here to stay as a strategy, or whether it's just going to be a short-term thing. But there's also, you know, I think things that we are all well aware of. It also this chapter also highlights the importance of external amenity space, biophilic design. It'll be interesting to understand, you know, whether that can also have a part to play in air quality within office spaces as we move on. And here is another case study. This, I think, was the first well gold or well platinum, I can't recall off the top of my head, office space for Hilson Moran in Manchester, and it does employ some of those key factors, such as sort of biophilic design. And one of the interesting things here is the additional monitoring that was required as part of the WELL standard also enabled them to find out that actually before any of the sort of BMS systems, they were able to discover that some of the mechanical equipment wasn't actually functioning as efficiently as it should have been. So that was really showing the benefit of that standard in practice. And then this is another sort of timber example, which we've got here just really to highlight the sort of well-being benefits of having timber, and there are plenty of studies which show how having that connection with a sort of natural material is a very positive thing to have in the workplace. And here the other aspect obviously is views out. This is an unusually idyllic spot that we've got here, but it goes to show those points. And over to Rob or Chris, I'm not sure.
Yeah, this was just really to discuss the role of engineers in terms of trying to gather data from our buildings. And I think certainly from a structural engineering point of view, we're probably not particularly good as an industry at actually learning from our projects. So not to dwell on this, but this is just 4 examples of where we are trying to, you know, embed certain processes, certain digital technology, or in the case of Google at King's Cross, where we have a hybrid structure of CLT planks and steel to build a prototype prior to the building of the actual project to test the dynamic performance of that hybrid system, because it's never been done before. There aren't any codes of practice, so a lot of this is you know, from first principles. So we're trying to kind of buck the trend in a way and actually try to learn from our buildings, so we don't have to start from scratch when we design the next one. And obviously a sustainable imperative. And Derek will probably talk a bit more about some of the other things that we can do in terms of measuring air quality and maybe sort of thermal imagery and all of that sort of thing, which, you know, post C19, I think is going to become far, far more important to all of us who work in any sort of communal buildings.
Okay, I'll take you through the last section now. We are probably running a little bit over. I'll try to speed things up a little bit, but we will continue, and everyone is free to stay on, even ask questions after. So chapter 6 is reuse, and that's what we're calling is basically adaptive reuse. And I think it's quite obvious, but you know, the most sustainable thing we can do is actually to reuse a building. And if we kind of just look at the UK and we look at, you know, the existing building stock, there's opportunities everywhere. You know, there's opportunities in all the different ranges, all the different categories. You know, you can't just kind of put them into categories. I think every building has its own challenges. And that's perhaps why you know, it's really important for kind of engineers and probably contractors to get into these existing buildings to assess them early. So if you just flip to the next slide, Ed, you know, we talk about this concept of potentially flipping around the organization of a design team for engineers to potentially take the lead in saying where the building massing should be extended and where it can't, because in the end, you know, it will come down to the cost and the value of that expansion. Obviously, one of the biggest difficulties we have is with existing buildings is when we don't have any records available. And so we have to go through this process of investigation, analyze, design. Then we go to the next step. We do some more investigations based on what we know, and we go through the process again. So it's very iterative process, and it's really important kind of for the design team to work in kind of an agile way. So the way the design team works is really important to kind of getting the best out of the building, let's say. We also need to obviously remember old materials, you know, don't change, but the way we analyze them and understand them has throughout the years. But can we expect that trend to continue? In my mind, I don't think so. And that's why obviously, you know, chapter 1, future proofing, is probably even more important now. We often obviously need to strengthen buildings, you know, and kind of early evaluation is key to that. And the level to which we need to strengthen it is really important. That's why accurate cost advice is absolutely essential to finding out which projects, you know, are viable and which ones aren't. You know, and it's about that early investigation. It's about finding that redundancy that really defines strategy. So if you go to the next slide, Ed, you know, there's all sorts of strategies, you know, retaining the envelope, going taller, expanding, infilling, you know, there's several. And then I'd just like to finish off kind of with 2 case studies that we looked at as part of this project. And the 2 case studies are at the total opposite ends of the spectrum. So the first one we looked at is 100 Liverpool Street. So this is a building obviously right near Liverpool Street Station here in central London. It's just finishing construction. And on this building, we were lucky enough actually to obtain 100% of the construction information, including all testing data as well. And so because of all of that, we were able to really kind of push the limits of this building. We ended up demolishing 50% of the building while adding an extra 45% beyond the existing NIA. And because of all that, we were able to save 7,300 tons of carbon. The second case study is, like I said, at the opposite end of the spectrum, where we had absolutely no structural information available. The only actually piece of information that was retrieved is that top right-hand photograph, which is effectively worthless in terms of structural engineering information. So this was a building where that, you know, that iterative design process and investigations was really key. But that, you know, opposite ends of the spectrum, you know, really does make you think where this world of BIM is headed. Is a BIM model going to be useful in 50, 60 years? Are they just going to be corrupted? Is that technology still going to be around? And perhaps maybe it's still better to actually just leave a set of archive information in the bottom of the building. So at this point, I'm going to hand it over to Derek, who's going to talk about different interesting materials developments. So alongside our paper, we do talk about all these exciting materials that are entering the industry at the moment. So over to you, Derek.
Thank you, Chris, and good morning, everyone. I've only got about 5 minutes to present a widening scope of materials which will become available, or most of them will, in the short and medium term. We now have the challenge of climate change, health and well-being, and of course these further complications since we last met on COVID-19, which I'll say a little bit about at the end. And because people spend most of their time in buildings, and they consume about 39% of the world emissions, They use 50% of the materials and generate 45% of waste. They're obviously extremely important. But then, not only that, we've heard a lot about their structural properties, a lot about their energy, either embodied or operational energy, but they also affect people's health and well-being. They emit substances which can pollute the environment. They have visual beauty, of course, but the textures are important too, because they have an enormous effect on the surface temperature inside the space, and also how much reverberant sound you get in the space. So they're critical on the inside and the outside of buildings in a most profound way. There's a move, as we've seen, Chris and Ed saying, to more off-site construction, more 3D printing buildings are becoming available. And of course, that has the advantage of less waste. But we also can remember that waste composites can be effective recycled materials. And in talking about the changing scene in materials, we shouldn't dispense with the material, the traditional materials like hemp, straw. We've heard a lot about wood already, concrete, and bricks. They all remain important. But these traditional materials can be modified to lower embodied energy and improve strengthening properties. And this is where we're seeing the field of physics, biology, materials science coming together in a much more integrated way. So, for example, there's a thing called concrete, which is reinforced, which is concrete reinforced with nanographene that improves the strength and lowers embodied energy. Wood waste has a substance called lignin in it, as you probably know. When you put wood fiber into concrete, it becomes stronger. Wood has a cellular structure, and if this is copied by a metal like, in this case, nickel, for example, we've got a very strong, interesting substance called metallic wood. Now, you can go on the inside of materials, and this embedding is most important. So embedment of graphene, waste fibers, but also digital devices. So you're beginning to see digital communicating devices within materials. And a big example of that is cybertecture, which is the brand of architecture designed by James Law in Hong Kong. And the famous example is the egg in Mumbai, and he has other examples too. We've got phase change materials, which help to control heating and cooling in spaces. And then the opposite to embedding is coating. You can actually have various films, and again, they can be graphene, they can be titanium dioxide, which interacts with ultraviolet light to clean buildings. And that obviously has an effect on pollution and also maintenance. There's a subject called photonics, which is dealing with coatings like hafnium oxide, which reflects so much of the solar radiation that, in fact, the surface remains cooler, and that saves on cooling loads, of course. Coatings can be put on to prevent corrosion. And it's probable, and I'll come to this again in a moment, they can be antiviral. Some mention's been mentioned of biophilic design as improving indoor air quality, but again, there's a wide range of opportunities in biophilia and biomimetics. So, for example, the BIQ algae facade designed by Arabs and a German company in Hamburg, 2013. So you actually harvest the algae, which shades the building. But when you then you harvest it, you get a biogas. There's another development some of you may not know about, but there's an artificial leaf being created in America by Nakara. And I'm at the moment looking at an artificial leaf facade which generates hydrogen. So in the future, one could see a hydrogen generating facade. And the hydrogen economy is very important to everything. We're also seeing a fusion of living and non-living things, and that might sound a bit strange, but for example, there are electric bricks which have been shown to work very well using the metabolic activity of bacteria. The self-healing concrete, where the crack with water activates bacteria to give limestone, repairing the crack. There's a super insulating aerogel becoming available, which mimics the fur of a polar bear. And as you probably know, the fur of a polar bear, their hairs actually have are hollowed out, so they're actually super insulating. Shape memory polymers are being developed at Texas A&M University, and these act like breathing walls. So there's a whole range of possibilities, which means the field of materials is becoming much broader. There's going to be much more availability of choice. So that's just a few conclusions, because I'm very happy to hear from any of you who want to email me with more details and questions, but we haven't got time to go into much more. But the conclusions are, so we can see the materials impact emissions, zero carbon, health, well-being, pollution, waste, and now we must add in infection risk. And already, I think Robert's said, we must have much more monitoring. It must be automatic, that when you're designing, planning a building, all the monitoring systems are in place. And now there's a wide range of really great monitoring systems which aren't all that expensive, which give us a lot of valuable data, which is going to be good. Now, let's come to COVID-19 briefly. As you know, it's transmitted by air and surfaces. And incidentally, the knowledge on this is increasing all the time. For example, MIT have found out that 2 meters parting isn't very good for sneezes. And when you sneeze, you probably sneeze the droplets further. So again, the information will be coming. You probably know that the Crick Institute in London, all the touch places have antiviral copper alloys. And it's possible that graphene coatings could disrupt virus and bacteria. And another point in furnishings, especially carpets and curtains, they harbor germs, allergens, and particles. So the changes are, I think, for COVID are going to mean that when we're looking at materials, we're going to have to be much more sensitive to the possibilities of antiviral materials. The space planning, a lot is being talked about already about this on the news and so on. So that is obviously going to feature. The cleaning processes, the actual times you clean, how you clean, what do you clean with? Ventilation's been mentioned. And, you know, we haven't bothered too much about the distribution of air. We like to have it fresh and move the air around. We talk about air movement. But we're going to have to know much more, and you can do this visually, see the patterns of air movement in a space to see how that can move, give enough momentum to clear the droplet clouds that are around. And there's filtration, of course, and that's going to be a big issue. Low humidities actually happen not just in the winter. I've had a whole week in West London of fairly low humidities. And in low humidities, the virus seems as though it seems to be more prevalent in that. So that's very important too. So there's a whole future. Now I feel optimistic. At the moment, I'm rewriting the review of 2016 on wearables in the workplace, and I can tell you over that 4 years where we are to now, the field has changed so rapidly, but I think COVID is going to enforce the fact that we need to monitor health. Monitoring health helps to prevent it spreading, it helps to save the NHS costs and so on. And we can now get glucose wearable sensors. And I think by the research I'm looking at the moment, I cannot tell you when this will happen, but I believe we're going to have immune sensor patches, which we can attach to see the strength of our immune system. And we're also going to have embediments sensors in our lungs. As we could see, if you want to be strong against viruses and bacteria, your immune system needs to be high and your lung conditions need to be in good condition. And I think by using that approach of sensors and more monitoring, this will help enormously the problems that we have today. So I think that's all I've got time to say. It's very brief, and I have to move over a lot of subjects, but I think it's now back to Rob.
Okay, thank you, Derek. Thanks, everyone. We've obviously overrun, and we've answered questions as we've gone, which I hope has been useful for everybody. I think Derek's summary there of materials and also our response to C19 has been very useful. I'd like to ask the panel one more question before we stop, which again is about C19, because obviously it's the elephant in the room. I'd like to ask maybe from an engineering perspective and also from an architectural perspective, how we think design is gonna have to respond to C19 for future office design.
Well, I've just said something, so I'll perhaps leave other people speak first and come in last, but okay.
I think that's on the spot there, Rob. I mean, potentially, certainly in the short, I think it's important probably to distinguish between sort of short term and long term. Obviously, in the short term, I think that there's going to be huge change. You know, the government's released some initial guidance on what that might look like, and I imagine that many people in those circumstances will still prefer to work from home, particularly if the kids aren't there, from my perspective. But in the long term, I think it will be interesting, and I think it probably just puts more of the kind of well agenda to the fore. I think you know, all those things about air quality and the ability to vary your space, be able to go outside, all of that sort of stuff, I think is going to just become more important. That would just be my starter.
Yes,
if I can just share my thoughts, I think it'll be interesting. Obviously, the whole social distancing, you know, everyone's spreading apart, teams maybe working on alternative days to kind of spread people out, more flexible days, working. But I think one of the interesting things, which maybe no one's speaking about yet, is upgrading MEP systems regarding ventilation. You know, getting those droplets out of the air before they can even spread. I'm no MEP engineer, and I don't know too much about it, but I think it's an area that hasn't been talked about yet, that we should all be kind of keen and watch out for.
I think also we're going to have to be open to some controversial areas. There is quite a lot of work now on the effect of ionizers, using ionizers, that it does decrease in infection risk. We're also, things like ultraviolet radiation, infiltration has often been spoken about and is used, but there's a lot of controversy around it. And we will need to be prepared to talk about those things, in addition to the things I listed at the end of my talk. Thank you.
Okay, great. I think the only thing I'd add is I think geometry will change. I think Chris is right. I think MEP systems will change. You might find that ceiling voids have to be deeper. So I think, you know, floor to floors are already increasing, or already have increased over the last decade. I personally think that they'll continue to increase. So I think that the overall geometry of design, that the mass of buildings will continue to grow to give this kind of agility. I also think that there generally doesn't ever seem to be enough generosity in circulation areas. You know, i.e. there's never enough stairs or lifts, or not enough people use the stairs, and we try quite hard with AHMM to try and locate stairs appropriately so that people do use them. But to be totally frank with you, even though it's well signposted in the white collar factory, the amount of people that get the lift to level 1 is unbelievable. So, you know, I think a lot of that will change now, but I think when we go back to the drawing board, it's those areas of circulation and communal areas which perhaps need to be more generous than the actual floor plates, which is what we obviously tend to focus on these days. Right, I'm going to close it there then, because we are 12 minutes overdue, and people are obviously dropping off. So thank you very much to the panelists. Thank you for the BCO for organising, and thank you to our 125 attendees. Really appreciate you giving up an hour of your day to listen to our thoughts. Thanks all.
Thank you.
Thank you, everybody.
Okay, goodbye, everybody.